Infinite series and convergence. In this video, we'll introduce the subject that we'll discuss in the following 3 or 5 videos. The subject deals with an important application of infinite sequences, the representation of infinite sums that we call infinite series. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. An infinite series is the sum of an infinite sequence of numbers. In contrast to an infinite sequence, which is an endless list of numbers, an infinite series is an endless sum of numbers. You can change any infinite sequence to an infinite series simply by changing the commas to plus signs. Sigma notation provides an explicit rule for generating the series. See the video that appears in the upper right corner to get the basics of sigma notation. If A sub n is an infinite sequence, then the sum of this infinite sequence of numbers is an infinite series, or just series. An infinite series is a series with an infinite number of terms. These sums continue forever and can increase without bounds. Since it is impossible to add up infinitely many numbers, the series may or may not have a finite sum. But we know that if the series has a finite number of terms, it is a simple matter to find the sum of the series by adding the terms. So if we wanted to sum up the terms of infinite series, we could start creating sums of a finite number of terms, called partial sums, and determine if the sequence of partial sums converges to a number. A partial sum is the sum of part of the sequence. That is, a partial sum is a sum of a finite number of terms in the series. Let's see one example to clarify the idea of partial sums. Let us try adding up the first few terms of the following series and see what happens. The first partial sum is just the first term on its own. If we add up the first 2 terms, we get the sum of the first 3 terms is. The sum of the first 4 terms is. The partial sums of a series form a new sequence, so we can turn the partial sums for this series into a sequence as follows. If the partial sums show a trend of convergence to some number L, then we have evidence that the series converges to L as well. And the limit of this new sequence, if it exists, defines the sum of the series. We are now ready to define convergence of an infinite series. Convergence of an infinite series. Consider an infinite series and the sequence of partial sums of the series. A series converges if and only if the sequence of its partial sums converges, and we define the sum of the infinite series to be the limit of the sequence of partial sums. Mathematically, we write: if the sequence of partial sums converges to S, then the series converges to S as well. For each series, use the sequence of partial sums to determine whether the series converges or diverges. Let's start with a series that we can easily determine if it is a convergent or divergent series. We start by writing the first few terms of the series. We know this series is divergent, but we follow step by step to show how the method works. We now do the same for the partial sums. That is, we write the first few terms of the partial sums, and then we search for a pattern. You should note that the series is an arithmetic series, and the formula for the partial sums is well known. We now take the limit. The sequence of partial sums is a divergent sequence because its limit does not exist. Then, the series is also divergent. In general, finding a formula for the general term in the sequence of partial sums is a very difficult process. But now, we are going to take a brief look at three special series. They are named special series because they are the only types of series that we will be looking at for which we will be able to get actual values for the series. The first family of series for which we can calculate the value with relative ease is the telescoping series. So let's get started. We need to find the formula for the partial sums. So we start by writing the first few terms of the series, and then we do the same for the partial sums. Notice that every term except the first and last term is cancelled. A telescoping series is one in which most of the terms cancel in each of the partial sums, leaving only some of the first terms and some of the last terms. As we can see, the formula for the general term in the sequence of partial sums is 1 minus the reciprocal of n. We now take the limit. The sequence of partial sums is a convergent sequence because its limit exists. Then the series is also convergent. The telescoping series is one of just a few infinite series for which we can easily calculate the sum. To solve item C, we need to find the formula for the partial sums. So we start by writing the first few terms of the series, and then we do the same for the partial sums. Notice that every term except the last term is cancelled. This is a telescoping series. As we can see, the formula for the general term in the sequence of partial sums is square root of n. We now take the limit. The sequence of partial sums is a divergent sequence because its limit does not exist. Then, the series is also divergent. Unfortunately, there's no test that tells us we have got a telescoping series right off the bat. But here's a little tip. When you are dealing with a rational series, try to simplify the rational expression using partial fraction decomposition. Because if the series is telescopic, the partial fractions make it clearer. Partial fractions are the fractions that are formed when a rational expression is split into two or more simpler fractions. To decompose a rational expression, we follow these steps. First, factor the denominator of the rational expression. Second, create new fractions, each having one of the original denominator's factors as its own denominator. Third, for the numerators of these new fractions, insert an expression that is 1 degree smaller than that of the denominator. In this case, the factors are linear, so we put a variable representing a constant. The numerators are the constants a and b. Fourth, we multiply through on both partial fractions by the denominator of the original fraction. This creates an expression on one side with a variable containing sum on the other side. Finally, we replace the coefficient variables with the values we just calculated. We need to find the formula for the partial sums. So we start by writing the first few terms of the series, and then we do the same for the partial sums. Notice that every term except the first and last term is cancelled. As we can see, the formula for the general term in the sequence of partial sums is 1 minus the reciprocal of n plus 1. We now take the limit. The sequence of partial sums is a convergent sequence because its limit exists. Then the series is also convergent. We are now going to treat the second special series called the geometric series. Since you may have already studied this type of series in pre-calculus or high school, I will leave the details of the geometric series to you. If you need a refresher, go back and review this topic by watching the video that appears in the upper right corner of the screen. A geometric series has the form. The formula for partial sums is very known. You should remember that A is the first term and R is the common ratio. The series will converge provided the partial sums form a convergent sequence. So let's take the limit of the partial sums. As we can see, the convergence of an infinite geometric series depends upon the value of its common ratio. This limit exists if and only if the absolute value of the common ratio is less than 1. In this case, the series will approach the first term divided by 1 minus the common ratio. In short, we can state that if the absolute value of the common ratio is less than 1, then the series converges to a finite value given as follows. Let's start with the first example in this video. We started by writing the first terms of the series. We can see that each term is multiplied by half to find the next consecutive term. So the first term is 1 and the common ratio is half. So this is a geometric series with the first term equal to 1 and the common ratio equal to half. Since the common ratio is between -1 and 1, the series does converge. We set up the formula to calculate the sum of the geometric series. We replace A with 1 and R with half. The sum of this geometric series is 2, so it converges. Let's see another example. This series doesn't really look like a geometric series. However, notice that both parts of the series term are numbers raised to a power. This means that it can be put in the form of a geometric series. In cases like these, we split the series into two other series to calculate the sum of each of the terms and then add them together. As we can see, both series have a common ratio less than 1, so they converge. We set up the formula to calculate the sum of each series, and then we add them together. The series converges. The third and final series that we are going to look at in this video is called the harmonic series. The harmonic series is the series of rational numbers with numerator 1 and integer denominator values that progressively increase. A harmonic series has the form: each term of the series, except the first, is the harmonic mean of its neighbors, hence its name. The harmonic series diverges. This seems strange considering the terms eventually get smaller and smaller. Since the sum of partial sums is increasing, we can conclude that the partial sums grow without limit. This is not proof, but it shows that the series diverges.